Michelle, will you share that with me too?
If you remind me what you're doing.
This is page 643, Tim? Page 643. Chris, is it
It's
on?
going.
Pardon?
It's going.
All right. We're going to finish up the chapter and do some demonstrations along the way. And we're going to begin with a demonstration that we did a couple of days ago. We took a wire and we wrapped it about 1,000 times. We didn't actually do it in front of you, but it came that way. About 1,000 turns of wire around a coil to make a coil. We passed electricity through it and we created what? An electromagnet. In other words, we're trying to show you that not only are there naturally occurring magnetic fields from natural magnets, the Earth itself being a natural magnet with a naturally occurring magnetic field, there are also minerals that, with a high iron content, that can act as magnets and can acquire a very small magnetic field around them by virtue of being in the Earth's magnetic field for a long period of time. And we can take pieces of this and use them as natural compasses. But we can also create magnetic fields as well. And in order to create magnetic fields, we had to have electricity going through a wire. We had to have charged particles, charge moving through a wire. And when the charge is moving through a wire, it creates a magnetic field. Now what you see here is Westminster Christian Academy's very first science fair experiment. Literally. Way back, this was the 3rd year of the school. The headmaster of the school, Mrs. Evelyn Downs, said, "We need to have a science fair. Do it." So we told all the kids in the school, there are about 100 or so, if you would like, we made it optional, if you would like, you can create a science fair project and you'll get credit for it and that kind of thing. And if it's good enough, maybe we'll enter it in the big local science fair that is held every late winter, early spring here in St. Louis. It usually was at Queenie Park. And this is the only one that came in. This is the original. After that, of course, we had to require it and have a substantial number of rules and guidelines to make it happen. The problem was when you had an entire school doing a science fair with maybe 2 science teachers, we would be up till 2 o'clock in the morning in the little half gym where the school used to be located at DePere Elementary, and grading all of these science fair projects. It was a lot of work. And we eventually dropped that and made it optional for people who actually wanted to participate for extra credit. In any case, I'm going to demonstrate this for you. I'm going to hook this up to our power supply.
Wait, if I turn in a big nail wrapped in wire, can I get extra credit?
Yes, you will get like 0.01 points extra credit.
Oh, I already got that extra credit. Okay. I'm good. Thanks.
And you'll notice that right now, not magnetic. If I turn this on, it is a little more magnetic.
So magnetic.
Okay, so I have an electromagnet. And actually the very first electromagnet I ever made for viewing was in 6th grade. In 6th grade, I went to a 6-room, 6th grade schoolhouse. It was built in like 1903 in a rural community right outside Pittsburgh. And I'm going to go ahead and turn this off. You can see now the electromagnetic field is gone. No more magnetism, no more paper clips. And we had a brand new teacher in the 6th grade. The other 5 teachers were all elderly ladies that ruled with an iron fist. The new teacher for 6th grade, maybe the previous 6th grade teacher finally died, I don't know. So here comes this new guy, fresh out of education school, and he is going to do have a science fair, which is a very radical idea. You weren't supposed to make school fun back then. So we had the science fair, and all the 6th graders made a science project, and I built a 5-foot robot, okay, in 6th grade, and one of the arms was an electromagnet. And it had a motor to move, and it had a buzzer for a voice, and it had light bulbs for eyes, it had a regular crane for the other arm, and he was so impressed he gave me a AAA, whatever that means. So that was my venture into robotics, way back when Isaac Asimov had barely printed out the rules for robots, if you know anything about Isaac Asimov and science fiction. So this actually was something that I had constructed way back in 6th grade. The guy that did this, who was a sophomore at the time, I think, was named Ralph Kelly. And his picture's on the wall there with our alumni. Any questions on this? So what we're observing then is when you have current going through a wire, you create a magnetic field. And you can prove that there's a magnetic field that has been created either by taking advantage of it with an electromagnet or by putting little teeny tiny compasses around the wire. Okay? And all the compasses will be deflected. And I'm going to do that demonstration after we finish the chapter, when we can bring the camera up here and look straight down so that you can see it. And we'll let Tim be our photographer. That should be interesting. All right? The point is that we've been investigating a relationship between magnetism, charge, and motion. And we've learned that if you provide a charge and you push it through a wire that's in a magnetic field, you get motion. We call that what? A motor. Okay? Let the camera show that this is an AP physics class. And it took them like 15 seconds to come up with that answer.
Wait, what was your question?
And in the next chapter, we'll be starting this on Monday, we are going to learn that if you move a wire in a magnetic field, you can induce a current in that wire. That we will call what? A generator. And now we've learned that if you push a charge through a wire, you can create the magnetic field. So with these 3 quantities varying 2 of the 3, you get the third. That's my point. They're all related. And there are a number of famous physicists, such as Michael Faraday, Hans Christian Ørsted. He was a Christian, but Michael Faraday was. And you can see that a lot of the research that was done involved these rather simple experiments, which were absolutely profound 150 years ago, and now have become the bedrock of modern technological society. We have motors and generators and electromagnets being used all over the place in many different ways. So, we now have another right-hand rule. We might ask ourselves this question: which side of this gigantic nail will be the North Pole, and which side will be the South Pole? And in order to figure that out, we're going to use our second right-hand rule. The first right-hand rule, you recall, I suggested you let your fingers be the magnetic field, going from north to south. North to south. Okay? Let your thumb be the direction of the charge. Then your palm represents the force that's going to deflect that charge, or deflect that wire that has the charge going through it. And remember the demonstration from earlier in the week when I had this thick wire going through this magnetic field? We turned the current on and the wire jumped. All right? Which is a very simplistic motor. So how are we going to predict which is the North Pole and which is the South Pole? And here's another reason why, contrary to the way the book has you set up the right-hand rule, the first one, this shows why I prefer to use fingers for the magnetic field, because in the second right-hand rule, your fingers again represent the magnetic field. Excuse me, I take that back. In this particular case, we're going to let our fingers represent the turns of wire. My bad. The turns of wire, going from positive to negative. So since my turns of wire are going around the nail like this, if I have the fingers representing the way in which the coil is wrapped around the nail, beginning with the positive, going to the negative, then my thumb is pointing to the North Pole. This would be the North Pole, the way that I have this electromagnet constructed. So this is right-hand rule number 2. Right-hand rule number 2. Now it works both ways. If you know the direction of the current, and this gets back to why I like the fingers to be the magnetic field, if your thumb is going in the direction of the current, then your fingers represent the direction of the magnetic field. Coming out of the board here, going into the board on the right. You see that? Right-handed rule. Any questions on that? You can tell by this picture that, again, we can simulate the magnetic field by capturing pieces of iron filings in that magnetic field. They create what gives the appearance of loops, just like our drawing can be. We can represent a magnetic field by a drawing using lines. The next question might be, how can I make that magnetic field stronger? How can I increase the strength of my electromagnet? If you go to a junkyard where there might be thousands and thousands of old wrecked cars, have you ever seen one of those? A lot of times when they move the cars around, they'll use a gigantic electromagnet, and they'll lift the entire car up with an electromagnet. How can we strengthen that magnetic field? Well, we can increase the current. Later on, we're going to talk about how you can increase the number of turns of wire, represented by a capital letter N for the number of turns of wire. Also, the strength of the magnetic field depends upon how close you are to that wire. We want to wrap the wires very, very tightly around this nail. Better yet, it would be nice to use a very, very thin wire. The thinner the wire, the closer the wire is going to be to the nail. The nail helps to concentrate the magnetic field, whereas if we didn't have the nail, we would still have an electromagnet, but it wouldn't be as concentrated, wouldn't be as strong. And so the farther away you get, 2 pi r, the farther away you get from your wire, the weaker the magnetic field will be. And by using a skinnier wire, you can stay closer to the iron nail, and your wires will be closer to each other, and you reduce the value of R, causing your magnetic field to be bigger. Here's my proportionality constant. This is a quantity that you will be investigating in tomorrow's lab. Okay? Called the permeability of free space. The permeability of free space. Now here's another scientist involved in the study of electricity. Andre Ampere, French guy. They always had the curly hair and everything. The Dutch guys, this guy really looks Dutch. Or at least Danish, Norwegian, that part of it, Scandinavian. The discussion in this part of the chapter, Ampere's law and the long straight wire, basically is the idea that you can derive this equation that we just showed you earlier by setting up a calculus kind of problem, which they're doing here. And we're not going to spend any time to talk about that. And one of the reasons for that, unfortunately, is we are on a very tight schedule because, remember this year we started school a week later in August than normal? Which means the AP exam is not a week later, it's the same time as it is every year. So we've actually lost 1 week of time to prepare for the AP. And the way I've mapped out the rest of the year, we will only have 1 day, the Monday before the AP exam, for class time for you to work on the AP. The rest is on your own.
Oh, I'll be here that Tuesday because I'm taking AP physics.
Oh, that's right. That's good. All right? Now,
Gonna be-
let's look at this problem right here. The magnetic field of a long wire. If you have just a straight wire, and let's say we're going from positive to negative, and you held a compass up to that wire, the compass would only show the Earth's north and south magnetic poles. But if current was going through this wire, you could deflect this compass, like I will demonstrate after we finish going over the chapter, and we can bring the camera up close for the people on the robotics trip. Okay? And so this says we have a long straight wire, carries a current of 5 amps, pretty hefty current, and we have a proton that's 4 meters. There's my proton with a positive charge. It's 4 meters away from the wire, traveling at a speed about 1,500 meters per second, parallel to the wire, and in the same direction as the current. Okay? It says find the magnitude and direction of the magnetic field created by the wire. Find the magnitude and direction of the magnetic force that the wire's magnetic field exerts on the proton. Okay? So, if we use our right-hand rule, and my thumb is showing the direction of the current in the wire. Everybody see that? My fingers naturally want to curl into the board on the right side of the wire and would come out of the board on the left side of the wire. Correct? Well, the proton is on the right side of the wire, so that's the only place where we're concerned about the magnetic field. So we draw an X because that's the tail end of an arrow, showing that the magnetic field is going into the board. Okay? Now, because the magnetic field is going into the board, now we're going to use our other right-hand rule. Okay? And we put our fingers into the board for the magnetic field. My thumb is the direction of my positive charge. And you can see that the palm of my hand represents the force that's going to push on the proton. And so my proton is going to be deflected as a result of the current going through this wire. Do you see that? We used both right-hand rules in this illustration. And of course we can calculate the magnitude of the magnetic field using the equation we talked about a few minutes ago. All right? The next part in the chapter says, what if we have two wires that are relatively close together? Close enough so that the magnetic field created by current going through one wire and the magnetic field created by current going through another wire, those two magnetic fields can affect each other. If they were too far apart, the magnetic field would diminish to something that is most basically negligible and no effect that one wire would have on another wire. But if the two wires are close enough together, the magnetic field of one and the magnetic field on the other can affect each wire. And if both wires are not stationary and able to move, you would actually see these wires either come together or be repelled. And so once again, if we take our right-hand rule and we say the current in, let's say current in wire number 1 is going from left to right. So I put my thumb from left to right. This requires my fingers to curl behind the board, okay? And so above this wire, the magnetic field is coming out at you, and below the wire, the magnetic field is going in to the board. So if we try to draw that, here my magnetic field is going into the board due to this wire. But due to this wire, the magnetic field above this wire is coming out of the board. So we represent that with a dot. So this magnetic field from this wire is going in, this magnetic field from this wire is going out. Guess what the wires do? Well, let's see here. We have two parallel wires. The the force is attractive because they're opposite. If we reverse the current in one, then they will be the same and they will repel. Do you see that? And how can we calculate one of those variables if we know the others? We would be using this equation, which is derived up here. This is typically the way in which it is expressed. Here's my force per unit length. This is the length over which the two wires are parallel to each other. Okay? And the force of attraction of one wire on the other during the length that the two wires are parallel obviously is proportional to the current in each wire. But it becomes weaker the greater the distance between the two wires. And if the distance is great enough, then my force is not detectable. Does it make sense? Notice again how we use the right-hand rule. This equation then also can become a way to define both an amp and a coulomb, which I'm only going to mention in passing. Now here's an interesting problem. We have two wires, each having a weight per unit length of a 10,000th of a Newton per meter. They're parallel with each other. One is above the other. We're assuming that the currents are equal in magnitude but opposite in direction. The wires are 0.10 meters apart. Find the current in the wires such that the magnetic field that is existing between the two wires negates the gravitational field. In other words, one wire is going to want to, if one wire is stationary, the other wire is going to want to fall down. But if we can repel it and counteract the gravitational field, it'll stay in place. You see that? You understand what the question is asking. We want these two forces to equal each other, the gravitational force and the force of attraction between the two wires to equal each other. The sum of the forces we want to equal 0. Or we could say the one force must equal the other force, which can be expressed this way. If you add mg to both sides, you have a magnetic field equaling the gravitational field, or force. Excuse me. And now we just plug our numbers in, and we find out that you need a current of about 7 amps in the wire to create a magnetic field sufficient to negate or cancel out or be equal and opposite to the force of gravity acting on that wire. Now, obviously the magnetic field around a wire is pretty minimal. Not much magnetic field. And before I go any further, let's suppose that I wanted to take a compass and see if I could find the magnetic field around this wire. I would turn this on, it's plugged in, and what do you think the compass would do? I'm being a little sneaky here because what kind of current is going through this wire when I turn it on? Alternating current. Things that you plug into the outlet, alternating currents, alternating 60 times a second, 60 hertz. And so your compass would be trying to change direction 60 times a second, which would be impossible. So that's why if you take a compass and try to see if there's a magnetic field around a wire through which alternating current is going, you get no results. So later, I'll use direct current. We have alternating current coming in, but we have direct current coming out, and the direct current, we're going to create a magnetic field. All right? But the magnetic field around a single wire is very, very minimal. So just like with the electromagnet, how can we increase the strength of the magnetic field? Wrap it around in a loop, many, 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 many times, preferably around something that will concentrate, so to speak, the magnetic field, such as a piece of iron or steel. And so what we're actually creating is an electromagnet. Now, the word an electromagnet is basically a coil of wire, but that is similar to the word solenoid. A solenoid is a coil of wire. Many, 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 many loops of wire. Those terms are all the same. So don't get flustered if you see the word solenoid, just think the word coil. All right? So, let's say we just have one loop. One loop. And let's say that the current is going counterclockwise. So if I take my thumb, and my thumb is going to be going counterclockwise, my fingers in the middle will be coming out of the board, and the fingers around the outside are going to be going into the board. In other words, north to south. I'm creating a magnetic field from the north to the south. You see that? It's going into the board there, and there, and there, and there, but it's coming out of the board in the middle. So just having a single loop enhances the magnetic field in the center of that loop. And having 2 loops, 10 loops, 100 loops, 1,000 loops makes the strength of that magnetic field greater and greater and greater, creating an electromagnetic field sufficient, for example, to lift a car at a junkyard. So when we come down here, you'll notice that the electromagnetic fields that we are creating are very similar to permanent magnets. This could even be the Earth. Of course, we would call that the magnetic South Pole and the magnetic North Pole. But you see that we can use the same kinds of lines to represent the Earth's magnetic field, the magnetic field around a permanent magnet, the magnetic field around a solenoid, a coil. Now in tomorrow's lab, you're going to be doing a lab involving a slinky, where the slinky will be your coil. And we'll be investigating the magnetic field inside and outside and on either side of the slinky. Next week's lab, you're going to be using permanent magnets. These are neodymium magnets that are really, really strong. When I show you those magnets next week, I can put one on top of my hand and one on the bottom, and the one on the bottom will be held in place because they're so strong. All right? Any questions here? How do we create the North Pole there? By having the current. If the current is going out, in on the right side of the board, on the picture, out on the other side, my thumb pointing up, North Pole. And here is that same equation you had earlier, close to it, but now we've added the letter N to represent the number of turns of wire. How can you double the magnetic field of an electromagnet? Double the number of turns of wire. So it doesn't take much current. Do you remember the demonstration we did 2 days ago, where we had that electromagnet, and all we were using was a rather old D-cell battery? We had very little voltage, we were getting very little current, but because we had at least 1,000 turns of wire, Joey was unable to pull them apart. Remember? Of course, Joey's wimp. I'll never watch the video.
It's true, though.
So here's the word solenoid. Right, Lynn, have you ever seen this word before? Solenoid is a coil of wire. This is a solenoid right there with the nail in the middle. All right? And it creates what we call an electromagnet. Now the challenge with drawing solenoids is you have to somehow simulate a wire coming out of the board, coming in, coming out, coming in on a two-dimensional surface. A little bit tricky trying to draw those things. And at any point along here, the current is either going in or coming out of the board at those spots. And we have the magnetic field concentrated in the center. And in this particular case, if the coil is coming around behind and coming out towards us, as it comes up and up, your thumb is pointing to the North Pole.
Will the magnetic field inside of those loops be concentrated like the exact center, or just like everywhere inside of it?
Well, it depends upon how uniformly well you have wrapped the wires.
Like if it was perfect.
Yes, it would be right down the center of it. And so once again, as you might expect, how strong of a magnet, of a electromagnet, or how strong will the electromagnetic field be? Its strength depends upon the current going through the wire, and it also depends upon the number of turns of wire and the length of that wire, and that is combined right here, the number of turns per unit length. If you can wrap very, very fine wire thousands and thousands and thousands of times, your N divided by L ratio will be quite a large number. Big, thick wires like this, not so much. You're not going to get a very big value of capital N divided by L for big, thick wires. So real electromagnets usually use very, very fine wire. And in fact, one of the problems here is that the thickness of this wire is to a great extent due to the insulation, the thick insulation around the wire, which forces the next layer of wire to be farther away from the center. So a lot of times you will see your wire not with a piece of plastic insulation wrapped around it or coating it, but it'll actually be maybe spray painted, a fine layer of paint. But you do have to have insulation, but by spraying a coating on that wire as an insulation, then the wires can be much, much closer together, and you can get a much greater capital N to L ratio. Now, unfortunately, the television set that I brought over from the old school to demonstrate some cool stuff at this point has disappeared. Somebody decided that, oh, who uses old-fashioned vacuum tube, cathode ray tube kinds of television sets anymore? So they must have thrown it out, thinking it was junk. Sorry about that. How many of you still have the old-fashioned type of television in your house? Anyone still got one?
I have one. I don't know, we don't use it though.
If someone has a small portable one and wanted to donate it to the school, that would be great. But the old-fashioned TV sets, basically, you create a beam of electrons that travel from the source, piece of metal down here, back here under high voltage, towards the screen. The screen was coated in chemical phosphors, and the phosphors would glow. And as the beam scans the surface very, very rapidly, it creates the images. You control where the beam strikes with electromagnets. You can make the beam go up or down, left or right, by controlling the magnetic field that the beam is going through. And so what I would do is I'd get the television set out, turn it on, you'd be watching, a soap opera probably during the day, and then I would take a magnet and go right over to the TV and distort the image, because I would be adding an additional magnetic field besides the natural one that's pre-tuned, and therefore the image would no longer look normal. It'd be like if you were to look at yourself at a carnival mirror that's curved, you would really create some interesting effects putting a magnet in the vicinity of these old-fashioned TVs. Now, if you did it to a color TV, you could permanently unalign the three beams for the three primary colors that are used, and you could wreck the color TV. But black and white TV, you could demonstrate it over and over and over again. Okay? Wrapping up here. So here it says we have a certain solenoid, a coil, 100 turns of wire. The wire has a length of 10 centimeters. Find a magnetic field inside the solenoid when it carries a current of ½ amp. What is the momentum of a proton? So you'll notice that we have 100 turns per tenth of a meter. So this gives us our value of n. Once we have n, we can plug it into the equation for calculating the strength of the magnetic field if we know the current, which we do. What does the capital letter T stand for? Do you remember? Tesla. And do you remember how many Teslas the Earth's magnetic field is?
0.5 times 10.
It was about 0.4, 0.5 times 10 to the minus 4. Okay? So we've created a magnetic field stronger than the Earth, probably by a factor of over 10. And then we take the strength of that magnetic field, bring it down to this equation, and this equation comes from setting centrifugal force equal to the force due to the object in the electromagnetic field, that proton. Once we get that value, then we can complete the problem. What was the second part of the problem? Find the momentum of the proton. And of course, the momentum here is represented. We let the letter P stand for momentum. Momentum is mass times velocity. Now you have the momentum of the proton. All right, Ampere's law applied to a solenoid. This is not covered that much in the AP, if I remember correctly. You recognize the terms there. I want to wrap things up by talking about why is it magnetic in the first place? Why is something magnetic in the first place? We're going to introduce a vocabulary word called magnetic domain. So, Chris, make sure the camera can focus over here. Let's look at iron. We're going to review a little bit of AP chemistry and honors chemistry. Iron, you can see, is element number 26. So it has 26 electrons, right? When we remember the orbitals and the energy levels that the electrons are in, to remember how we would put the first 2 electrons in the first energy level, S subshell, one going clockwise, one going counterclockwise in the only orbital, which is spherical. Then we go to the second energy level because the first energy level is filled. The second energy level has 2 subshells, the S subshell and the P subshell. The S subshell, of course, is another sphere, only one orbital, 2 electrons per orbital. Remember, you can only, if you have one electron in an orbital spinning one way, the other electron has to be spinning the other way. It's the only way you can get 2 electrons in an orbital is by them having opposite spin, because opposite spin create opposite magnetic fields. Remember that? Otherwise, the 2 electrons would repel each other. And you offset the natural repulsion of 2 electrons in the same region of space by having opposite spin. Remember the p orbital, p subshell has 3 orbitals along the x, the y, and the z, so it can hold 6 electrons. 2, 4, 6 is 10. We've taken care of 10 of the 26. If you're following along in the periodic table, we're now up to the third energy level, 3s, 3p, the 3d. Again, this is going to be a 2 and a 6. But if you're following the periodic table, when we get to element number 18, which fills up the 3p, that's argon. But what element comes after argon? Potassium, element 19. And that's not in the P block. That's back in the S block. So we start to fill up the 4s before we fill up the 3d. Do you have happy memories of chemistry? So we're going to put 2 in the 4s, representing potassium and calcium. And now when we talk about iron, we've got 1, 2, 3, 4, 5, 6 electrons for the 3d subshell. Now, we're going to take this information, and I'm going to abbreviate it with just argon. Remember argon in brackets, and then we're going to have everything past argon, which is 3d 3d6 4s2. Okay? And now I'm going to represent my 5 orbitals in the d subshell. Here is a single orbital of the s subshell. 1, 2 electrons. And now we come to the d subshell. Remember, you put 1 electron in each orbital before you fill up the second? Like the Monopoly game, you build 1 house in each property before you put the second. 1, 2, 3, 4, 5, 6. Now you notice we have 4 orbitals, each with a single electron. And an unpaired electron creates its own magnetic field. Because an electron is a charged particle, the charged particle is moving, it can move in 2 different ways. It can move translationally, but it can also spin. Either one is going to create a magnetic field. And so these 4 electrons can actually, if they're all spinning in the same direction, and again here we're using the model of an electron being a particle as opposed to a wave. We're not going to get that far into quantum theory. If these 4 electrons are spinning in the same direction, you get an enhanced magnetic field. Now, if we have thousands and thousands and millions and trillions and moles of electrons in a big chunk of iron, if we can get all the electrons spinning in the same direction, now you begin to get a magnetic field that is measurable, that is easy to detect. And a large region of electrons spinning in the same direction is called our domain, a magnetic domain. Okay? And so, here is a big chunk of metal, but each region of metal has a bunch of electrons spinning in the same direction, but not similar to the other regions of metal. Here, all the domains are canceling each other out. So the chunk of metal is non-magnetic. However, if we put that piece of metal into a strong magnetic field, or we force a strong current to go through that metal, we can gradually get all of the domains to begin to point in the same direction, creating a stronger and stronger magnet. Now, some materials can become permanently magnetized. And they've been in our cabinet over there in the physics lab for years and years and years, and they're still magnetic when you take them out. Other cheaper magnets, after they get dropped and banged around and played with by freshmen and so forth, or an AP physics student who will go nameless, says he's not here. But it's possible for all those domains that used to be aligned through wear and tear and dropping and hitting and so forth to become unaligned, and it loses its magnetic field.
So what happened to my fridge magnets?
Pardon?
So what happened to my fridge magnets, like the leather magnets? They don't stick anymore.
But we do have a device that if you have a bar magnet, it's designed to reestablish the magnetic field of that bar magnet. I don't have it out with me right at the moment. I've often magnetized a screwdriver so I could fish out a piece of metal, that I couldn't get with my hand somewhere. But if you drop the screwdriver on the sidewalk, for example, or on the basement floor, it loses its magnetic properties because the domains have all become unaligned. Does that make sense? A few other vocabulary words here. The word ferromagnetic. Maybe you recognize ferro comes from the Latin word for iron. Remember, we often talk about the iron 2 and the iron 3. Is the camera facing back from here now? We often talk about iron 2 plus and iron 3 plus. Ferrous and ferric were the old-fashioned names. We now just call it Roman numeral 2 and Roman numeral 3. But it comes from the Latin word for iron. And many, many, many magnets are mostly iron. We have some magnets called alnico magnets. They're mostly iron, but they also contain aluminum, nickel, and cobalt. See this? Alnico magnets. And the aluminum, cobalt, and nickel keep them from rusting and provide some physical strength, because iron can be a bit on the soft side. Now we're using rare earth elements to create these neodymium magnets that are extremely powerful, as you will see next week. Okay? Now here's two other words to go with ferromagnetic. Ferromagnetic, the atoms have a permanent magnetic domain. Paramagnetic is very, very weak. Extremely weak. Nevertheless, there is a magnetic field. If you think about it, lots of your transition metals probably have one or two or three orbitals with a single electron in them. They're just not as strong as iron. And then diamagnetic is where there's an actual weak repulsion. Any other questions? Okay, Tim, bring the camera up here. Now come up here and I'll show you a few things. Here's the Ralph Kelly Memorial Magnet. But this time, you can see that I've created a magnet. If I come to the other side, the red end points. All right. The next thing that we're going to do is turn off the electricity, put a magnet here. You'll notice right now it's aligned in the Earth's magnetic field, north and south. When I turn the power on, all right, let's do it this way. There we go. I'm trying to put natural north and south. Now when I turn it on, see it go perpendicular? When I turn it off, the magnetic field is lost around those wires. And of course, if I reverse, now we should see the compass do what?
Go the other way.
Opposite direction. Okay? The last thing that I wanted to show you was an electric motor. Remember, we said that if you have a magnetic field represented by these magnetic disks on either side that are black, and if we have a power supply to push a charge through the wires, and we've enhanced that effect by having coils, we get motion. You might notice the little sparks. See the sparks? Yeah. That, of course, is where the charge is jumping from the commutator to the brush. The brush are the... Let me turn this off for a second so that we can see the brush. Bring it around here. Here's the brush right there that rubs up against the split ring commutator. And the reason the commutator is split is so at the precise moment when this coil has passed through the magnetic field in one direction and now is going to go through the opposite side, which would technically cause a reversal, we are also reversing the direction of the charge, the electrical charge that is going through the coil. And so if I unhook these, we can make it go in the opposite direction. And you can make very, very simple motors just using paper clips and a V-cell. They did it in freshman physics. Any other questions? Everybody say goodbye.
Goodbye.